Hey everyone, so I'm back again with another Euclidean geometry proof. This time we're going to do a proof called the proportionality theorem in triangles. So this is the one that's related to the one I did before called the midpoint theorem. So it's taught in grade 12 and this is what it says. So it says if a line parallel to one side of a triangle intersects the other two sides of the triangle, then the line divides these two sides proportionally. Okay, so say we have a triangle and let's name it A, B, and C. Then we have D on AB and E on AC, so that when we join the 2 points, we have them line parallel to BC. So this point D and E, they're not necessarily halfway through between A and B or A and C. It could be anywhere. It could be a line coming from here to here or over there, from there to there. This is not exactly like the midpoint theorem. That's why we're saying the midpoint theorem is the special case of this one. So this line could have been anywhere along the point, the line, the side of this triangle AB. Okay, so let's go on. So what we're required to prove is that the line segment AD divided by DB, well, the ratio that we get is the same as AE divided by EC. So that's what we're going to prove. So to prove this, we'll say prove, then we join B and E, then we join D and C. Now, after doing that, we see that we come up with triangles. So these highlighted blue triangles, actually 3 triangles. We have this ADE, we have DBE, and the big one ABE. So if you see this, if you look at this, we have the same height for them if we choose a height from this side of the triangle. So let's draw H1, a height for all these 3 blue triangles. Okay. Next, the same thing we will do on the other side. The red part that I've highlighted has made 3 triangles, DEC, ADE, and the big one, ADC. So again, if we draw a height from D perpendicular to AE, it will be a height for all these 3 triangles. Then we'll call it H2. Now, the next thing that we will do is we'll look for the area. We're going to use the areas of the triangles to come up with the ratios. So now we're looking for area of triangle ADE, which is this triangle here, divided by area of DBE, which is this triangle here. Now, since they are part of those first blue triangles that we talked about, it means we can use H1 for their height and AD and DB as the basis for the 2 triangles respectively. So this becomes half AD times H1 and half DB times H2. Then we see that here H1 and H1 will cancel, the halves will cancel. We're left with a simple fraction of AD over DB. This is because we have the same altitudes. Altitude is just another word for height. So that's the height of the two triangles. Okay, next we'll go to the other side where we highlighted red triangles. So here we have ADE again, but this time we're going to use the red height to calculate its area, and then ECD, which is this one. Then again, it shares the same height, the red height with ADE. So it means we can write that as half AE multiplied by H2 over half EC multiplied by H2. Then again, the heights cancel, the halves cancel. We're left with a fraction of AE over EC. Same reasoning, same altitudes. Okay. Now we notice that in the two ratios, how we came up with them, we used the same triangle ADE in the first, the blue triangles, and again we used ADE. So we're sure that this is the same area. So for the two ratios to be equal, we just need to show that these two, the denominator areas, are also equal. So let's look at the two triangles. We have this one, which is ECD, triangle ECD, and we have this one, which is DBE. Now, if you look at them and forget about using this side as the height and this side as the height for ECD, we are now going to choose DE to be the base. No, let me correct myself. We're no longer using DB as the base and EC as the base for these two triangles. We're going to use DE as the base. So when this one is the base, it means the perpendicular height from DE all the way to this point. Perpendicular height for both of them will be the same thing since they're between parallel lines. Then it means they have the same base DE, and then they have the same height since they are in parallel lines. So it means their areas will be exactly the same, because we will say half DE multiplied by the same height for each of them when we're calculating the area. So it means that we have shown that the area of this triangle and this triangle, the area of the denominator triangles, are going to be equal as well. So we say the area of DBE is equals to the area of ECD. And this is because they have the same base DE and the same height since they are in parallel lines. And finally, since we've proved that the denominators are equal and the numerator is actually the same triangle, we can conclude that the ratio of ADE over DBE equals to the ratio of ADE over ECD, which means these two ratios here are finally equal to each other. Okay, so that is how we proved that these two ratios are equal. Okay, now I have drawn the same diagram in GeoGebra just to show or verify that the proof holds. The proof is true no matter how the shape is. And we're going to show that this line doesn't even have to be halfway, like in the theorem, midpoint theorem. So as you can see, we have AD, which is this distance, divided by DB, which is this distance. And this is the value of AD. You'll see it changes when we move the points around. And this is the value for DB. Again, on the right hand side, the red side, we have AE divided by EC. And these are the values, and this is the final answer for the ratio. So this, even if we change the shape of the triangle. The lengths will change, but the ratios remain the same and they are equal to each other. So even if we move this point DE, as long as it stays parallel to BC, then the ratio that we get the same value for AD over DB and for AE over AC. So we move this down here, it doesn't matter where the line DE is, as long as it's parallel to BC, then we will have the same ratio for the two. Right, so please like and subscribe and write in the comments what else you would want to see me prove for you, and I will see you in the next video.